The notion of a function is one of the most important in all of mathematics. So in this video, we're going to ask and answer the question, what is a function? And hopefully shed some light on why functions are such important objects and tools. When you were growing up, it's possible that your parents took you aside from time to time and measured your height against a wall in your house. If that's the case, then what your parents would have been doing is associating to various ages that you had over time. Those ages could just be numbers indicating years. Your heights at those ages. Your height h at a given age a is an example of a function. And using mathematical notation, we would denote it by the letter h followed by the letter a in parentheses, which is pronounced h of a. For another example, imagine a car driving down a straight stretch of road. As long as the road is being modeled by a straight line, we can go ahead and identify the road with the real number line itself, and therefore associate different real numbers to different positions on the road. And what you might then do is associate to a given moment in time, t, the position of the car at that moment in time. Or you could try to measure the car's velocity at a given moment of time. And here too create an association where at a given moment of time, we associate to it the velocity of the car at that moment of time. Here, position and velocity are also examples of functions, in this case denoted s of t and v of t. Consider a circle of radius r. It's natural to ask the question, given that the radius of the circle is equal to r, what's the area of the circle? Here too we have a function on our hands, namely the function that assigns to a given positive radius the corresponding area of a circle of radius r, which we're here denoting a of r. In fact, you probably already know how to describe that area via a formula. So here's an example of a function that can be presented as a formula. We would say that the area of the circle for a given radius r is equal to pi r squared. And one final example, suppose you go to the grocery store to pick up a few things. What you'll of course notice is that every item in the store that's for sale has a particular price, p, associated to it. So here too, inside of any grocery store or any store whatsoever, there will be a natural function at play, namely the function that assigns to any item its corresponding price, p of I. If we try to step back and formalize what's common to all of these examples, then we arrive at the definition of what mathematicians call a function, and it is certainly one of the most important definitions in mathematics. It says that a function is a rule that assigns to any element of some set A exactly one element of some set B. And we express this using the following notation, which says that f is a function from A to B. It's important to note that the sets A and B don't have to be different. They could be the exact same set, so it's allowed that A equals B. And here the letter f is the name of the function. It is the name of the rule that assigns elements of B to elements in A. And here A and B, of course, are two sets. In practice, the sets we'll be working with will be sets of real numbers, but in principle, the sets could contain absolutely any sorts of elements. One convenient way to picture a function between two sets A and B is by representing the sets as abstract blobs. So let's suppose that the set A consists of 6 elements represented by the white dots, and that the set B consists of 4 elements represented by the black dots. Then for every element in the set A, we can simply draw an arrow from that element to the element in the set B the function f associates with it. And in this way, we produce a nice picture, or if you like, diagram of our function. This diagram here, of course, just represents one particular example of a function from the set A to the set B. Let's have a look at another abstract diagram. Suppose at this time the sets A and B each contain exactly 3 elements. And suppose that we draw arrows from A to B in the following way. Does this diagram represent the diagram of a function? Well, this time the answer is no, and that's because the definition of a function is being violated here. The problem is that there's an element of the set A which is being associated to two different elements of the set B. So there are two outgoing arrows from that middle element in the set A to two different elements of B. Recall that by definition, a function must assign exactly one element of B to every element of A. After seeing the abstract and formal definition of a function and studying those abstract diagrams, the definition of a function might seem a little unintuitive or idiosyncratic, but let's look back at our real-life examples to see how it actually makes a lot of sense. Notice, for instance, that it is impossible for you to have two different heights at the exact same age, A. Right? On the other hand, at every single age, you have exactly one height. A car driving down the street has exactly one position at any given moment of time, right? So there's a function here. And notice how indeed it simply wouldn't make sense for a car to have two different positions at the exact same moment of time. Likewise, a circle of a given radius will have exactly one area. It is impossible for a circle of a fixed radius to have two different areas, right? That just doesn't make any sense. And finally, a given item in a grocery store can of course have only one price associated to it. It doesn't make sense for one item to have two different prices. It's perfectly possible, of course, for two different items to have the same price, but once again, it doesn't make sense for one item to have two different prices. The definition of a function, like most definitions in mathematics, is truly inspired by real life. And once you go looking for functions out there in the real world, you will start to notice that they're all around you. Let's take another look at a general function diagram and give some more names to what we see. If a given element in the set A is denoted x, then the value that f assigns to x is denoted f of x. We might think of x as a variable that's allowed to range over all possible elements in the set A. It represents, as it were, the input of the function f. And f of x can be thought of as a variable that ranges over some of the elements of the set B, and it can be thought of as the output of the function f. It's often convenient, in turn, to denote the output of the function by its own variable. Let's call it y. And in that case, we would say that y is a function of x, or that y equals f of x. We would call x the independent variable here, and y would be called the dependent variable. And the reason for this bit of terminology is very straightforward. The variable x is allowed to be any element of the set A. It doesn't depend on anything. Once x is determined, however, then there's a unique y value associated to it. So the variable y does indeed depend on x, hence it is the dependent variable. Now in practice, we will be concerned almost exclusively with functions that take values in the real number line and that are defined on subsets I of the real number line. And these subsets will usually be intervals or possibly just the real line itself. As such, it's often possible to represent a function via operations that can be performed on real numbers. So, for example, it's possible to take an arbitrary real number x and add 1 to it. And we can represent this by the formula f of x equals x plus 1. Or we can take an arbitrary real number, let's call it r, and square it, and then multiply the result by pi. Right, so here too is an example of a function that can be represented as a formula. And of course, this is just the formula for the area of a circle. And finally, here's an example of a piecewise function called p of x that's defined by two different algebraic formulas on two different pieces of the real line. The piece where x is greater than or equal to 0, and the piece where x is less than 0. If someone were to ask us for the values of these functions at the input 1, then all we would need to do is substitute x or r equals 1 into the corresponding expressions that define the functions. So for example, f at the input 1 would of course just be equal to 1 plus 1, which is 2. The function a at the input r equals 1 would be equal to pi times 1 squared, which is just pi. And finally, the function p at the input 1. And here we'd have to look and make sure that we're working on the piece of the real line where x is greater than or equal to 0, would be equal to 2 plus the positive square root of 1, which is 3.